Yeah, we'll have to get started. I think the other people probably will be late and it's recorded, so they will be able to watch the video later. And there are some important updates I want to let you guys know. If you refresh the web page, you will see the remaining tasks for the rest of the semester. And today, we're going to introduce UART, which is a very important serial communication protocol. You'll use it a lot in microcontrollers. And here we just, it's very exciting because we are touching the very bottom protocol of the logic. So you'll see what's really happening. And whenever you are downloading a Arduino script onto your Arduino board, it's actually communicating through TX and RX, which is UART. It's a universal asynchronous receiver and transmitter. Whenever people talk about serial, it's usually referring to UART if they're not specifying some other serial protocols. If they just say serial, it's usually just UART. Okay, it's the most commonly used digital protocol, communication protocol. And so this one, so you are not supposed to work during the break, right? But if you want, you can. So the task is not due until the week, the week 11. So after spring break, still have 1 week to work on it, and it's due on Tuesday after that week. So I have the whole entire week to deal with it. And then tomorrow is Friday, so I'm not expecting you guys to, work really hard. Sometimes you have to take the fly in somewhere else. So I have 1 day, 2 days this week to, if you still have time, you can work on it. And also you have the entire week after the spring break, plus the weekend, plus the Monday and Tuesday, okay? So this one is due April the 1st. And on that day, so on Tuesday in that week, I will cover another very exciting and important topic. It's not a real world SoC design. I'm higher. But it's very similar, but it's a simplified version. So when you are thinking about SoC design in Qualcomm or Apple or any other, there's a huge market regarding SoC design, which is system on chip. Not every company is making ASICs, which is doing the layouts and fabricating chips, which cost a lot of money for the company to prototype one IC design, usually like millions of dollars for the 20 nanometer technology usually. So it's a lot of money. And if they have a bug on the chip, probably $2 million is gone. That's the reality. So usually they prototype SoCs on FPGAs first before they send it out for fabrication. So that's why FPGA is getting so popular. If you are only good at FPGAs, you can get a job. Usually it pays you $120,000 at the start, and usually can go up to $200,000, after 5 years. There are just so many jobs. And so what do they do in the company? So they have FPGA, and eventually, for example, the Snapdragon CPU used for Samsung, they are using ARM cores. It's not the Pico Blaze core we are using for Basys board, but it's going to be a very sophisticated CPU. Usually it's ARM. There are so many different versions of ARMs. And the ARM is written in RTL, which is a registered transistor level, which is verilog. It's just a huge verilog code, which is the ARM core, the CPU. And what do they do? So the ARM core is a module. They have that module loaded, like adding a source, right? Adding the source to the design environment. And it has a name for the module, like ARM Cortex 7 or something. And in their top module, which is a whole chip, they just instantiate the ARM core in there and have all the pins. There will be like thousands of pins, not like the 5 or 6 in your example, thousands of pins, being shorted to other modules in the top. And you may have memory files is another module you have instantiate, so you have to declare wires to make the interconnections. That's how they design SoCs. It's very similar, but it's going to take a year for us to do ARM core, and we don't have ARM core. We cannot afford it. It's just too expensive. So there are many open source cores, starting from the easiest one, I think will be the best example to work on. Again, it's very exciting. I mean, this can be the starting point for you guys to start an SoC career. Who knows? So the CPUs or the core, the CPU core's name is called Pico Blaze. It has a Pico in the name, so you'll know it's tiny. And it's an 8-bit CPU. You can instantiate it in your Vivado design environment, and you can preload you can compile your assembly code and put it into the ROM and synthesize the ROM with your CPU at the same time. So it's gonna eventually give you a design to implement it on the FPGA. So what is that final product? Just think about it. You have instructions. So what are instructions? Like the C++ code you code it up in Arduino. You're making a loop. You're adding something to somewhere. You're like making conditions, conditional statements, things like that. So these are instructions. But for C++, it's being used. It's a higher level instruction. It's easier to understand and read. So you can definitely understand other people's code and easily. The compiler is going to compile it into machine code, which are 0 and 1s, and being stored in the ROM memory. So definitely we don't have a C or C++ compiler for our Pico Blaze. It's just too simple. But what we have is assembly code. It's not C++, not C, but assembly. So assembly is a nightmare. There are so many people started a computer engineering career in the college trying to learn it, but stopped at assembly because it's just it's a nightmare. It's not fun. It's not readable usually. But if you read it, blinking LED takes you 2 hours, but it's just not fun. However, not every environment will allow you to code it up in C++. So the engineers make it so simple to code up, to use, like the Arduinos, you just load the library, because they spend so much time to make it work for you. But however, for a lot of design projects, you are probably the first person to work on it. I mean, how can I expect that there will be an Arduino environment for you to code it in C++? It's impossible. So a lot of cases, as an SoC engineer in the company, probably you are doing assembly at the very beginning to test all the things, right? So here it's a little bit longer than a week, okay? And you have a lab on it as well. Very extensive, so be careful. Try to spend some time if you are new to assembly. But you probably have learning in computer architecture. Have you? If you are taking it, you will learn it. It's going to be a different instruction set, which means so the instruction set has a corresponding hardware, because you must have the hardware like an adder, so you can add something in assembly. When you are adding something, it's actually taking the adder's functional block to do that computation. So, for example, this Pico Blaze is actually a microcontroller. You can imagine that. So it's a microcontroller. It has all the peripherals and has a CPU core. And when you are instantiating that Pico Blaze, it's called KCP SM6. When you instantiate it in your Vivado environment, it's actually placing a microcontroller on FPGA. You synthesize everything with the instructions, which is not C++, but instructions in assembly, as is telling the CPU to do what, right? Taking the switches and display on Samsung displays, and for all these executions, you need the instructions. So the instructions are being written in assembly. They are both synthesized together onto the FPGA. So after the implementation, the little Pico Blaze microcontroller on your Basys board is something very similar to Arduino. So you are making a real product. It's not ready to be sold yet, but it's a microcontroller. So that's why I think this is a really exciting project. It's pretty long, and you have to learn assembly first. before you get into it. Second, just make you, so I want to talk about this earlier because you need to prepare for it. That's why I have to bring that up today. So if you have time, try to read the chapters on the book. It's not on the book I require for this class. It's another textbook. You don't have to learn all the other chapters. It's very similar to our textbook, but the author really did a really good job on KCP SM6, which is a pickle place for these chapters. They have awesome examples and repeatable. And this is priceless. So I searched for a while. I couldn't find a third textbook can do the same job. So the one you have now is a simpler version, and the examples actually you can download from GitHub. If you search for the examples on the book, you can find it. And these examples, I think 99%. I found one bug in one listing, but for most of them they work really well. So the textbook has examples, work really well together. So it's not a joke. It's working. It's a working examples. And same for this textbook. If you scroll down on this tutorial, at the very bottom, I have all these links for you guys. So first, you can click this. So the author's name is Peng Chu. So Peng Chu's code for the book examples. So it's gonna guide you to the GitHub link. It has a VHDL version, has a verilog version. You want to use the verilog version, and it has all the critical listings on the book in here, so you don't have to type up everything by yourself. Second, I highly recommend you. So it's not wasting your money. Buy the book on Amazon or somewhere else. It can be a used one, doesn't matter. But that book really has a lot of very good examples and repeatable. Okay, so here's a link to the book. So luckily, it's not that very expensive. If I use one, only $60-something. Okay, buy it definitely. All right, and the reason I recommend you buy it because most of the examples or the assembly chapters, you need to read it through for a lot of times. If you just since I have some of the chapters, I just put them together in one PDF. And have the link on the website. But sometimes it's one chapter, a couple pages here, a couple pages there. You don't have the big picture of the whole book. So definitely buy it. It's really helpful. And another thing is the book used an older version of Pickle Blaze, which is called KCP-SM3. However, the newest version released, I think last year in September, was KCP-SM6, not 3. So we want to use a newer one. But the problem is, if you directly use the examples on the book, it's not going to work for these examples. So it's a bit challenging. You have to modify part of the code and to make it work, which is a good thing because you can take that chance to try to understand the code more deeply. Okay, so a couple of things as a summary. First, buy the book. Okay, and second, if you have time, try to read these chapters, the assembly chapters, ahead, so you can prepare for that. I think you only have like 9-10 days to get all the things done, and at the same time, you have a lab, so it's very intense. And after that, so after the spring break and a week after that, it's not going to be 1 week tutorials. So for example, I have a tutorial here, I'm going to introduce it here. So I'm going to do Thursday next week. It won't be 1 week. Same for the USB version. So it's being covered on Thursday, but it's due Tuesday after a week. Okay, so probably have like 10 days or so, a little bit over 10 days to work on it. And there might be a project I'm still considering if I should add it here. Considering the workload for the whole class, they have a lab as well. So probably there will be a small project to be added to the labs as lab 9 or something if I want to, but depends on your progress. Okay. One more thing. So when you are doing this one, you may need a faster turnaround time. So you know how it works when you are programming a microcontroller using C++, right? So you usually change the code and you click upload, it's gonna do the job in like 3 seconds. It's not the case here. It takes like 3-5 minutes for every time. However, when you are trying to debug your assembly code, it's like debugging a software. And a lot of times it won't work. So I have to resynthesize everything, and it takes such a long time to develop a design here. So, if you have to, if you can, just probably use the 2018 version of Vivado. It's a little bit faster. You must find a faster way to do it. Otherwise, it's going to take, if it takes me like 3 hours to complete all the tasks, it's probably going to take you 2 days. The turnaround time is so long. That's another thing you need to be aware of. Okay. So today's lecture is a UART. Important. The protocol is very simple. That's why it's just being used everywhere. You definitely have RxTX on Arduino, right? Remember? So there's a IoT project right after the spring break. It's going to let you use the RX and TX to communicate with a Wi-Fi module. So it's very commonly used. It's everywhere. And the protocol is super simple. Look at this. How many pins do you have for UART? This can be on the interview. I mean, so for all these topics I cover in this class, it's different from a math class or physics, right? It's going to be on the interview, and you're going to use it for regular work if you get a job in the digital design company, which is everywhere. Okay, UART as well, important. Okay, so how many pins are there? 2. TXRX, that's it. You don't even need the power. You don't even need the power for the communication. The power is powering up the devices, but not the module here individually. That's incorrect because they must have a VDD and ground inside, right? There's all these transistors and digital blocks. They are powered and grounded. And however, for the communication, you only need 2 pins, 2 wires. It's a single bit for each wire. RX, TX, TX, RX, there are no difference. They are exactly the same modules. You don't need to make it different in the transmitter and the receiver because both devices have both modules. It has RX. RX is receiving something, so it's a receiver. It must have a TX as well, which the transmitter is sending bits out. So there are only 2 lines. Okay, and here's the protocol, and that's it. That's a timing diagram. That's it. So you are thinking like, if this is for RX and TX here, so what's the one here? I mean, you have 2 lines, but you only have 1 timing diagram. I mean, does that make sense? What's happening? Candles, yeah, it's the same protocol. It's only 1 wire. For example, I'm doing this one, right? Okay, I'm doing TX here and RX here. It's only 1 wire. So that's why you only have 1 waveform here. You cannot handle another one. It's only 1 bit. So what's happening is the sender has a high at the very beginning. So if the sender has a high, what this one receives? No, a high, because it's only 1 wire. Again, just keep in mind, with just 1 wire, if the sender pull it up, you think you can keep it low here? No, it's going to short the VD to the ground. So you only have 1 signal. If it's just 1 metal wire, you pull it up, here will be up as well. So that's why you are seeing just 1 line, just 1 timing diagram. So at the very beginning, the sender pull it up. And whenever this is put down to the ground, it's a signal bit to get things started. So the receiver is going to sense that voltage low, and it's going to know that data is going to come in at the next clock cycle. So the LSB, you see D0 here, so LSB is being sent first until the MSB. And parity bit is optional, you don't have to, but eventually, after everything is done, what's going to happen? How do you signal a stop? How do you tell the receiver? So for example, it's actually a communication between devices, but you can imagine that as similar as I'm talking to Max, for example. Okay, I'm trying to send you information, which is a bits is a byte, right? If I'm keep talking, how do you know where the byte gets started? You don't know. I'm keep talking, right? These are just 2 words. Is a byte I want to send to you, but I'm keep talking. I have so many bytes, you don't know which one is a byte I want to send to you. So I have to pull it down first. So it's sensing a 0 first. I keep high here, so you are receiving the same wire. I pull it down first, so you know it's getting started. But that 0 bit, which is the starting bit, is not a signal. There's no data in there. So you can see here, it's just a start. It's just a 1 bit, 1 clock cycle. It's not. There's no information. Just a start bit. So I have to pull it down first, like I tell Max, here's the information. And then next will be the information, like go lunch or listen or something like that, right? So this start, so D0 can be 1, can be 0, but that's information. And after that, all the A bits are information. But I want to tell you, like, where is the end of the information so I can start another one, right? So the sender has to pull it up to stop, to pull it up to signal a stop. And then the receiver knows these are all the A bits I should receive. I will put in a memory bank, which is A bit, and then I'm going to write it to the next one and put it to another byte. How that works. You are thinking, I mean, how do you know it's a stop bit? It's just a regular bit. It can be a data 1, right? How do you know it's a stop? If a counter, you know where to start. So start has to be low. So after the start bits being received, you just count by 8 times, right? You know, it's going to be put up anyway, but you know that these are all the A bits I need, and then I'll be ready for the next. However, whenever it's put up too high, so the sender won't send any other data anymore. It's going to be a stop bit, but not data. Okay, that's how the 2 devices manage the communication. And this one is optional. So in the TX, in the transmitter example in the tutorial, we didn't use a parity, but in the receiver, we do use a parity bit. I'm going to show you really quick. So there are 2 examples, 2 main examples in the tutorial. First is a TX module is a transmitter. So how that works. So what I did here is, so Arduino serial monitor is just a serial monitor. It doesn't have to work with Arduino. Okay, so I'm using an Arduino serial monitor, but you can use a different serial monitor terminal. You can find it everywhere. But you can use Arduino serial monitor to receive all these signals. So what I did is, so the core UART transmitter module is just example from the textbook. Okay, you can directly copy and paste. And what I managed, you know, what I did over here is the top module, not this one, but this one, the top module, is sending strings to the TX module. I want to show it here. So here's a system block. I just want to give an overview of it first. So the TX module is over here. It will be implemented on the IPGA. And you have 5 push buttons on the IPGA board. So these can be used as a signal inputs. So, but you have to debounce it. So there's a debounce module is very simple, just use it, right? So it's going to give you a clear rising edge, okay? So whenever you push it, it's going to give a clear push button output, and that output will send a signal from the UART to the serial monitor, which is a Arduino serial monitor. So you don't have an input for what's the data you want to send. It's directly a rag data type in the top module. For example, it's the A, right? I want to send an A to it. So the A will be an 8-bit signal, which is a hex number, which is 41. Why is 41? It's an ASC2 code. You have to look at the table here. So in the serial protocol, all these symbols and letters and numbers, all these kind of things are represented by 8-bit ASC2 code. For example, where's A? It's here, right? That's a character, and the code, the ASC2 code for that is 41, so which is 01000001. That's a hex number. And there are other symbols. So if you send 23, it's going to show a hashtag, so forth. So you can look at the table and for what you want to send to it. So for the top module here for this example, what I did is every time it senses a push, not this one, sorry. Every time it senses the push, it's adding 1 to the hex number. So you can explore all these characters on the table, right? Just adding 1, just keep showing all these symbols. So there's no other input. So the input is going to be a rag tab data type and holding a as an initial value there and keep adding. So you don't have another interface like a switch, right? I want to use a switch to input a 41. No, it's just push it and then it's going to keep adding to the initial value to show these symbols and characters. Does that make sense? Okay, and let's see how this works really quick. So that's a transmitter. That's a transmitter you want to use for the push button example. First, UART you have used in microcontrollers. The baud rate is 9600. Usually, you don't have to use 9600 definitely, because as long as the sender and receiver has the same baud rate, they will communicate properly. You can imagine, I'm sending this signal here, like according to this table, this waveform at 9600 bits per second. The receiver thinks that I'm sending at 11500 bits per second, right? So it's gonna skipping these bits because it's sampling faster. So that won't work. You have to match. So if you are using 9600 in your FPGA, in your serial monitor at the very bottom, you have to change it to 9600. Keep in mind. However, the parameter in the submodule can be override by the top. So that's the first parameter in the module, right? See, there's no other parameters above it. So this is the first parameter, and when you are overriding it in the top module, it's actually here. See, UART. So this is how I instantiate that UART, and I use this hashtag parentheses, and I put a new number here. Put a new hashtag, new baud rate over here. So by default, it's going to override the first parameter. But you can override more parameters. So the way you do it is just for the first one, comma, and keep doing that. So it's going to override all the other ones. But in this example, it's just trying to show you that you can do it. So in the top module, I actually changed the baud rate to this. Okay, so this will be taken into the sub module and replace this number with a higher baud rate, just to let you know. So this is actually not doing the job. So that's why for the counter, right, that's the 100 megahertz clock from the board. And if I use this one divided by this variable in the real application, in the real implementation, it's actually dividing by bigger number, not the small number. So that's why you want to use a variable here, but not 9600. If you use 9600, it's not going to change it. It's still a number. So a quick question here. Why this should be the number of the timer? Why should I set the timer to be this? We're using 9600 now, okay? So here's a clock. Clock. So you are using a positive edge clock. So this clock is 100 megahertz. But however, you want to send every bit at a rate of 9600 instead of 100 mega. Okay, so you want to count until this number, then do something. Okay, why is this number? Because this is using 100 mega divided by 9600. You can imagine this is 1 second. Okay, this is a 1 second time frame. And for the 100 megahertz, it has 100 mega counts in this time frame. If I divide it into 9600 pieces, I just need to count until every single piece and do something. So in 1 second, I'm going to do it for 9600 times. So that's why this is how you do it. You use this number divided by 9600, you can get the counts, the max counts you want to use. And there are 1, 2, 3, 4, 3, not 4, 3 states. So I only need 2 bits, 0, 0, 0, 1, 1, 0, good enough for 3 states. So the first state is ready, so which means it's not sending any bits. It's just ready for receiving another, to send another bit. So because when you are sending, it's only one line. When sending every single bit, it takes 8 times. So you need a ready state to tell someone like I'm ready to send another byte. So the ready state is doing some initiating job. What this does is it's clearing out the index, which is the 8-bit or the byte holding all the data in there. So you want to clear it to the first, like a pointer, you clear it to the first index, to the first LSB, so you can keep inserting data into it, into the byte, and clear the timer, and send the 1 to TX bit. So the TX bit is actually the output, 1 bit, 1 line, the output. It's directly shorted to the output on the top module. So when you are initiating that UART, you want to send a 1 to it because you want to pull it up too high. Remember the protocol? It's not starting yet. It's just getting ready to send, but not started yet. So I want to pull it high. So what's next? So the module, the UART module has a send bit. It's a command telling the UART module to send something, start sending things out. This is another input for the UART module. So if that command is being set or is 1, then you put 0 as LSB and 1 as MSB and data in the middle. So it's a 10-bit data. Why? Why is that? So the UART is not always sending, right? So now the UART is ready to send something. So whenever the send command is 1, it's start doing the job. But it should make the data ready first. So all the bits should be in the 10-bit bank, data bank or memory bank. Why 10 bits? Why not 1 byte? Start and stop bits, right? So I have 2 bits. So start bit definitely is 0. It was put to 1. That's why you need a 0. Whenever it starts sending the LSB, it's directly get a 1. and then followed by the data starting from D0 to D7, and then stop. So got 10 bits to be sent. So you got the 10 bits ready, and then transfer the state to the next. So whenever the next rising edge arrives, it's going to directly get into here and to the counter, to the timer thing. So you need the timer to time up to order timer, which is this one, right? That's a max count. It needs to be counted to that max number, and then clear the counter, no problem, and change the state. So next rising edge is going to transfer to the other state, and send the LSB to the output wire. So what is the LSB now? For the first time it gets into here, what's the LSB in the data? There, yeah, here. So it's going to start. It's a start bit. The first time it gets into here, it's going to start the communication. And then adding the index. So next time it's going to send the next one, but not keep sending the start bit. It's going to be the data next time, right? And then else, if it reaches the max, then do this. Otherwise, keep counting until like the ball timer here, right? So next time it's getting to here. Send the bit, okay? If it reaches the index max, which is number 10, which is bit 9, it should be done for the 10-bit transmission. So it should get back to ready. So it's ready for the next one. Otherwise, come back to low bit for the next for the next bit in the 10-bit bank. Okay. These are all the 3 bits. That's it. Very simple for the transmitter. And by default, it should be at a ready state, so it's ready to send something. You know, that's kind of like standby state. It's always there if there's nothing other happens. And also, it should assign the output to another, because this text bit is always being manipulated, so it shouldn't be used as the final output. So you should do this another step to send it to the final output, which is UART, which is the 1-bit output. It's TX, right? TX is 1 bit for the output. And this one, so stay equals ready, yes or no, right? Yes is 1. 1 will be assigned to ready. No, it's going to be a 0. 0 will be sent to ready. So yeah, we haven't used this statement in, it's probably different in C++, but you know, it's a conditional statement. So stay equals ready. If it's at ready state, then it's going to be a 1. So 1 will be assigned to ready. Okay. If stay is not at the RDY state, so 0. So 0 will be assigned to ready. So what is ready? Ready is the output for the UART module. It's telling the outside world if it's in the middle of sending something or it's ready to do something else. Right? If it's in the standby state, it should be ready to send another byte or another 10 bits. So that's everything for the transmitter. It's very simple. And the bounce circuit, it's keep detecting the button. If it's not, so if the button has some changes, so the state change, even though it's bouncing back and forth, so there will be some change. And then clear the counter, you know, start to wait for another period of time, which is 6.5 milliseconds. So it's like it keeps sensing the button, right? If there's still a vibration, then clear the counter and wait. Still vibration, clear the counter and wait. Until there's no vibration anymore for 6.5 milliseconds, it's going to reach, just not clearing anymore, right? It's going to do this. So the current state will be assigned to the button. If it's high, it will be high. So it's going to give you a clear high from the button. Just debouncing the vibrations. There are not another sub module for the top, so just need the debounce and the UARTX, and that's it. So you do the top module here, can directly Just use whatever I have. You don't have to modify anything for this task. So the top module has three states. It's from the textbook, but I don't think, you see, BNT wait, BNT send, and BNT send wait, three states. I have gone through the script for a few times, but I don't think the third state is being used at all. I mean, it's a bug in the textbook. It's not going to affect anything because it's not getting into that state. So whatever you put in the state, it's fine. It's just not being executed. So the default state is BNT wait, is button wait, is waiting for any changes. See? So the debouncing circuit is going to give you a clear button output. So if it's 1, it's clear, right? And the previous was 0, which means there's a push. You want to send something. So it's getting into button send, and it's going to assign the initial string or character to the UART data, which is just a bit, right? So the a bit will be from the top, will be directly sent to here, to the input of the UART module, and then doing all this serial communication by the sub module. So this sub module will take care of everything. You don't need to worry about it. You just need to give all the 8-bit data to it, right, from the top. And next time it's going to add 1 to it. So if A is the first one, B will be the next, and then keep going. And then come back to button wait. So wait for another push. So I just couldn't find not anywhere or any reason that the state will jump into the last one. So it's not going to get into the last one. So I recommend you try to delete it. Copy and paste all the script over here and delete this one and see if that works. I think it should work the same way. Okay, this is the result. You want to show the same result as pushing. Show a video on all of it, right? So you're pushing your FPGA, but now you're Arduino. I'm kidding, I trust you guys. So push your Basys 3 and show these on the Arduino serial monitor. All right, see, this has been changed because I override it in the top. So here's a middle one you want to push, but you can use other ones. I don't really care. It's just different name for the constraint file. And the receiver, a little bit longer, but very similar concept. So there's something like can be a little bit difficult to understand. So that's why I think it's going to be beneficial to be in the class today. So here's the receivers module. It has more states. That's why you need 3 bits for all the states. Ready, start, receive, wait, check. There must be another way to do it, but this is just directly the example from the textbook you can play with. And let's see. So the TX is being shorted to the RX of the receiver. It's the same line again, same wire. So this is being sent from the transmitter, and it's going to be the same thing being received at the receiver. The receiver is seeing the same thing. That's why when you are doing the receiver's verilog, see, what is this? So the TX from the transmitter is shorted to the RX of the receiver. So why I have this here? It begins at start bit. So whenever the transmitter pull it down to 0, the receiver will receive that 0 immediately, right? So just one wire. That's why when RX is 0, it starts doing something. It wants to change the state to start. And at the same time, clear the index for the whole bank. So next time it's going to start saving from the LSB, saving the bit into the LSB of the data being received. So here's something like can be confusing. So when it gets into the start state, the timer counts to 50% of the maximum count and do something, and then count to the max again. So why is that? So whenever it gets started, so it transfers to the start date and only counts to 50% of the max. And then do these things, but still not saving any data to the bank. Just clearing out all the bytes or bits, like resetting everything. And then get into here, then you count to max again, and then start saving. See, start receiving the bits. Why is that? Whenever I got started, I receive the start bit. I know the next clock cycle is going to be the data, right? So what's the problem here? So keep in mind the non-blocking are being executed at the same time. So whenever it reaches here, it's going to do this and this at the same time, and then it jumps to start and doing all these resetting or initializing, initialization for all the bits. It only counts to 50%. So 50, after the start bit, for example, we are looking at this as a receiver, right? After this falling edge, the receiver counts to here, the middle, 50%, to reset everything. And then count to another period or the max to start receiving data. So my question is, does that make sense? And why? So what's happening is actually perfect.
So the TX and RX, they're sharing the same line. So TX is sending this, and RX will see this at the same time. So after it is being pulled down to 0, immediately start the counter. It counts to 50% of the max to reset everything, and then start counting to another full max, 100% max, to start receiving the data. Does that make sense? Yes, it's right in the middle of D0. You don't want to receive data here. It might hit the edge and give you a wrong data. You don't want to receive it here. You just want to receive it in the middle. That's just the best situation. Right? You don't want to receive the 0 that started as a data. So that's why whenever it hits 50% of the max count, you don't want to do anything. You don't want to save it. It's just a 0 bit from the start bit. It's initialize everything and count for another max to get this one. And then start counting to max. So eventually you get all the data not getting this one. Okay. That's why it has to count to 50% first.
Count to 50% first, and then count to the max to receive the real data, but not the start bit. And right in the middle, keep in mind, right in the middle, that will be the best place to sample it. Okay. So now let's come back to the receivers module. Whenever it receives a start bit, jump to start, jump to here, all right? And then when the timer is 50%, clear out everything, and then jump to wait. And when wait comes to the max, it's right in the middle of D0, clear the counter. If ready, if you already received 8 bits, done. Move to RDY state to the very top. Otherwise, start receiving after that. Because right now I'm right in the middle of D0. I want to start sample it. So get into receive. D0 here being stored in that location, which is LSB. And then increment the index by 1, so it's moving to D1. D1's location. Next time it's going to receive D1 and save it there. Okay. It's jumping back to wait, not to ready, because it doesn't want another start bit. It's keep receiving all the D1 until D7. And once it receives, so once the index hits number 8, it should jump to check. So why do you have number 8? Keep in mind, so in this example, we do have a parity bit. So number 8. So you have 0 to 7, which are the 1 byte of data. So number 8 is parity bit. You're asking like, where's start bit and stop bit? Why it becomes 8 instead of 10 this time? The TX is sending 10 bits, start, stop data, right? 10 bits. But why I'm counting to 8, not like 11? Why I'm not using the 11th bit as a parity, but the receiver is not receiving the start and stop bit. It's just skipping them, it's detecting them and start receiving the data. So for the data being received, you only have 8 bits, but not other bits. So the parity bit, there's a parity bit over here because I'm going to use a terminal, a serial terminal like this. It's not Arduino terminal anymore. So you are setting an even parity bit over here. So whenever I type, so this is on your laptop, right? So I open up this terminal and I set up these things, and I also set up a parity, which is the even parity bit. So it's going to send 9 bits every time, actually. So you type something in the terminal, and it's going to send that one combined with 1 parity. So your IPGA will receive 9 bits from bit 0 to bit 8. So bit 8 will be the parity bit. So that's why when in your verilog, you can actually check it. So whenever it reaches whenever it reaches 8, so you know it's right at the parity bit now. So you want to go to check. So how do you do check? So the RX stored all the bits in that byte. It has 8 bits in there for the data, and you do XOR. So this is a new operator, a new form of XOR logic. So XOR this thing is actually XORing every single bit together. So bit 8 is a parity bit, right? For example, if I have even number of ones in here, what is the result for this operation? Even number of ones in 1 byte, and I XOR every single bit together. So what's the result? 0. Okay. If that is 0, and it's an even number of ones in there, do I need a parity bit to be 1? I already have even number of ones in there. Do I need a parity bit to be 1 to make it even? No. So this one will be 0. So if I have even number of ones in the byte, I XOR them, I'm getting 0, and it equals 0, so no error. Let's take another example. If I have odd number of ones in the data, I XOR them together, what I'm getting? 1. I have odd number of ones in there. Do I need a parity bit to be 1 to make it even? Yes. So this will be 1. So 1 will be 1 as well. 1 equals to 1. If that happens, no error. Otherwise, error. Okay? So the receiver should output an error bit. It's in the else case, right? Else. Error should be 1. It should indicate that there's an error happening. But however, because everything is being integrated in the IPGA, so there's no chance to get an error. So the error bit should be always 0. Unless you have some like electromagnetic interference to flip the bits from the wireless way. Otherwise, it's going to be always off for the indicator. And so all the results are being shown because the IPGA this time is the receiver transmitter this time. Question, is IPGA a receiver transmitter in this example? Receiver, so what is the transmitter? The laptop. You have a terminal, you have a serial terminal downloaded. It's called like what kind of terminal, and you can even set up even parity bit in there. So you type A in the terminal, you press send on your keyboard or the laptop. It's gonna send that thing through the USB and send to your IPGA. So IPGA is the receiver, and you have a question like, it's a USB cable, why is UART? So the IPGA is connected to the laptop using USB. Why is RxTX? Why is UART? There's a USB to UART converter on the board. It's the same as your Arduino. The little chip right behind that USB port is a USB to UART converter. So it's doing UART, and you should have that terminal and shoot a video. So this is the final result. So the LED A bits, lower A bits, are showing the ASP2 code from the terminal on the laptop, right? So that's the data being received. So you can see, what is this? 3-1. That's 3-1. Come on, 3-1, right? 3-1, and you refer to the ASP2 table, and you will know like what I just typed in there. I typed 1. So sending 3-1 to here, and I can receive 3-1. And here's a parity bit to make it even. I have 3 1s here, so it has to be 1 to make it even. And there's no error. And this is how many numbers I have typed, I have sent. So it's counting. This is just the first one. And then I typed 2. And so that's why it's the second data to be received. This is counting becomes 1 0. This is 1 here. And so, oh, sorry. Anyway, I probably typed the 2 first. I don't know. Oh, I typed 1 again. I put a 1 there again. So it's receiving a 1 again, but it counts incremented by 1. Why do I keep pressing 1s? So that's why I'm asking you guys to type a 2 there. So you should, if you type a 2, you're expecting 3-2, okay? And for the tasks, first, it's not related to UART, it's just a debunk circuit. I want to use the debunk circuit to create something really similar to the problem in the midterm of 351. You push the push button, and the Samsung display is going to show how many pushes you have done, okay? And less than 10, because I don't want to make it complicated. So I have to switch in between 2 Samsung displays. And the second one, repeat the transmitter, and third one, repeat the receiver, are simple, just copy and paste. And the fourth one is asking you to show the numbers you typed in the serial monitor, which is the IPGA has to be in the receiver mode, right? It receives whatever you typed in there and display it on the Samsung display. It must be something you can display on it, right? You cannot just type a hashtag. There's no way to display it. So just show a couple examples like ABC or 1, 2, 3 like that. So I did the first. So I think the first 3 ones are pretty simple, and the last one I haven't done that yet. You probably need to spend some time on it. So do it early. Any other questions? One thing I'm running out of time, so I didn't prepare that tutorial for you. I think that'll be really fun because right now it's the IPGA UART module is interfacing with your laptop. But what I'm thinking is, since you have RX and TX, but Basys 3 is running at 3.3 volts. Your Arduino is running at 5 volts, so you cannot directly connect your TX to RX on Arduino and RX to TX as well. It's going to blow off your Basys 3. So you need a level converter, which is really, really good experiment actually. So you can learn how to use it. Grab a little module, can convert 3 volts to 5 volts, 5 volts to 3.3 volts. This is not damaging anyone. And communicate with an embedded system instead of a laptop. So you have your Arduino here, level shifter, step down the voltage to 3.3, have the RPGA, has a UART module on it, and try to send something to the Arduino and display it on anything. Doesn't have to be laptop, it means something else. That'll be another really interesting test as well. But we don't have it this time. So these are all the tasks you are supposed to work on. Just spend the time on it. No questions?